Hi, my name is Ryan Rosani and now present our paper, GP-S3Net, Graph-Based Panoptic Sparse Semantic Segmentation Network. This work was carried out at Huawei Noah's Ark Lab in collaboration with Ran Cheng, Engshu Li, Ehson Tagavi, Yuan Ren, and Bingbing Liu. Recently, panoptic segmentation has begun to receive broad research interest. Panoptic segmentation is an integrated task of both static environmental understanding and dynamic object identification, in which both semantic and instance segmentation tasks are unified. Some existing panoptic segmentation methods transform 3D LiDAR point cloud into 2D image using spherical projections in perspective or bird's eye view, which abandons valuable 3D geometric structures and suffers from information loss due to projection process. Recent proposal-free methods request point embedding and form instances by clustering. But clustering is not ideal for segmenting objects, as it is a deterministic process. Although a handful of methods have been introduced to address LiDAR point cloud panoptic segmentation, but the question of is there a way to integrate independent semantic segmentation and target recognition into a system so that the instance level segmentation of objects can effectively use the result of semantic segmentation has not been addressed adequately in the literature. To this end, we propose an effective proposal-free LiDAR-based panoptic segmentation network called GP-S3Net. The overall pipeline of our proposed method is shown here. It includes a semantic segmentation backbone followed by a graph-based instance segmentation network and panoptic fusion. The final output is panoptically labeled point cloud in which every point has both a semantic and an instance label. Our new design consists of a novel instance-level network to process the semantic results by constructing a graph convolutional network to identify objects which later on are fused with the background classes. This approach has turned an unsupervised clustering task into a supervised graph edge classification problem where edges between two nodes indicate whether they belong to the same instance. So let's look at the detailed instance segmentation of GP-S3Net. First, over-segmentation priors are generated by running HDB scan clustering on foreground predictions. Next, these priors are passed to a 3D convolutional layer and are embedded into a unified vector size. Each cluster is treated as a node in the graph, and its corresponding embedding is used as its node's feature. These features are then fed into a fully connected GCNN model called EdgeNet to predict the edge class for each cluster pair. Finally, the edge predictions are passed to the merge cluster node block to create the instance information. Note that EdgeNet is supervised with edge labels only during training, as shown in the red dashed box. Here is a comparison of different models with GP-S3Net on 3 different datasets of semantic kitty, nuisance, and semantic pause. Red circles demonstrate that the proposed method outperforms recent state-of-the-art methods. The numerical comparison of top existing techniques on semantic kitty are shown in table 1 and 2 here. For each table, the best achieved accuracy is highlighted among different methods. It can be observed that GP-S3Net outperforms the state-of-the-art approaches and achieves first ranking on the competitive public semantic kitty leaderboard with 60% PQ. Table 3 and 4 here show superior performance of GP-S3Net compared to all existing methods on nuisance and semantic pause respectively. Thank you.